Okay, so this presentation is about some RX listener performance tuning that we had done. This is a bit longer than the other ones that I've done so far, so I just wanted to mention the general structure we're going to be following. So I'm going to start out just with some background on the problem, our problem definition, because we are talking about a specific scenario here, and then we look at the baseline performance that we get in this situation, which for our hardware is between 1 and 2 gigabit. And we're going to look at approximately 4 different areas that are causing some limitations here. And for each one, just discuss the background a little bit, show the proposed solution that I've developed, and to see what the effects are on the benchmark that we have. By the time we get to the end, the last one will be exceeding 10 gigabit. And at that point, I'll go into some other considerations, some other effects in this area, and some other some stuff we want to kind of go do in the future. Is there a problem with the display? Okay. Okay, so the problem that we're dealing with was there was a customer site where there was an incident with a volume that was not very large, but not one of the tiny volumes that's just like a bunch of symlinks or something like that. So we'll say it's about a 1 gig volume. That's not the exact size, but just as an example to have a similar volume. And the files inside of it are all at least 1 megabyte large. Files over 1 megabyte usually don't matter because clients, of course, fetch files in chunks, and the chunk size is around a megabyte at the largest. So we're going to say we have a 1 gig volume. We have 1 meg files. We have hundreds of clients. All of them are accessing the data in this volume pretty constantly. So most of the time, all that data is cached. But when the volume is released, all of them try to access the volume all at the same time for all of the data that's in the volume. And when that happens, we get a file server that is pretty heavily saturated. So we see the number of calls waiting rises pretty high. The latency for all the calls to it, the file server seems very slow. You can still get requests through, but it's not an ideal situation. And if you think about if we can only push, we can't push more than 2 gigabits, this situation is going to last for like 10 minutes. If we have only 100 clients and there's only 1 gig of data, you do that at about 1.5 gigabits, you're going to have the file server in that scenario for almost 10 minutes. If we could improve that to say 10 gigabits, it would drop down to under 2 minutes. So there's a lot of things to consider with the different parts of AFS. There's a lot of moving pieces. There's a lot of stuff to consider. So for the purposes of this talk and for the improvements that we were making, there's a lot of things that we're ignoring. So for this, we don't care about the single client performance. That is, we don't care about the performance of individual clients, how fast they go. So a lot of things with the protocol of RX, things like window size or things like the window size of the packets and stuff like that, we don't really care so much about because we have so much stuff happening in parallel. We don't care about things like uncached files, meaning cached at the OS layer, that is stuff in BicePA that's cached, and we don't care about bringing volumes online. We're not really worried about other files. We're really just hitting a small subset of total files on the machine, and we're hitting them like quite a lot. So from that perspective, things are a very ideal situation. Everything is in memory. Things should go very quickly. We're not interested in very complex solutions to this problem. Other people have heard me talk about DPF and TCP stuff over the years. We're not doing stuff like that. We're trying to see what simple changes we can make to RX to get some big effects out of it, things that we can just deploy just as like fixes. It's not like a whole new major version of AFS. We're not trying to do a big transition here. These are just seeing what we can do that's pretty easy. We're also not concerned with the other servers in the system. AFS, of course, is a big distributed system. We're supposed to be pretty reliable. So if one file server is slow or if one file server goes down, obviously that's not the end of the world. We have other servers we can contact. Clients do fail over to other file servers. That's, I guess, not the problem we're dealing with. So if you want 10 times as much bandwidth, you can, of course, add 10 file servers and distribute and release the volume to there, and the clients will spread themselves out. But even if you do that, each file server is still only pushing 2 gigabits. Why can't we use the rest of our resources? We have more network throughput that we can use. Maybe like our servers themselves, maybe they have a lot of CPU, but we're still only pushing about this much. So we'd like to improve that even if we did add servers. So to do this, we have a test environment and a benchmark. I'm going to be showing actual numbers that I achieved with various changes to the code. So I want to just say what our hardware is, because obviously you have faster hardware, you're going to get better numbers. If you have worse hardware, you're going to get worse numbers. Our file server in this case is running Solaris 11.4. It's running on bare metal on a machine that's not like super powerful, but it's it's a normal machine. We're not running these on my laptop on an old Core 2 Duo, things like that. So I don't know. It's I don't know if that's like mid, low end. I was surprised to see on the Sunrise status report that is the same model, which I didn't know until today. But its processor, we have 8 cores or 16, virtual cores, 16 with hyperthreading, 16 threads, however you call that. And our clients are on a separate machine, which is running actually running a more powerful machine. Originally, I would have liked the file server to be running on the more powerful box, but Solaris does not run on that hardware. It's not on the hardware compatibility list, even though it looks very similar, Gen 9, Gen 10. And between the two, we have a couple of 10 gig NICs, Broadcom, whatever number. So our ceiling of performance is around 20 gigabit. We're combining the 2 NICs. It's not actually using bonding right now. It's kind of in a way that's sort of synthetic, so not actually applicable to how you would actually set up a network in the real world. But that's not too relevant. It's just it's set up that way so that we don't hit the limit of a single 10 gig NIC. Because if we do run these tests with one 10 gig NIC, we do pretty much saturate it, and I wanted to see how high we go. The harness that we're using, the thing to drive the tests and run them all, is just a Python script that I wrote for this purpose. It's called AFS CP Bench. It's not pushed anywhere right now, so I'm sorry. If we push it somewhere, that's maybe what it will be called. I wasn't really sure where to put it. I don't know if this goes in AFS contrib or we want this in the tree or whatnot, but we can discuss that at some point. But enough of that. Let's get some numbers. So this graph, we're going to be plotting some more lines on here. This is our baseline, what our starting point is. So we are running the master branch, which is current. It was current as of maybe a couple weeks ago or so. I don't remember what that, that's the commit SHA-1 up there. So you can get that. Okay. Yeah. I mean, it's hex. So, so in the master, in the unmodified master, we get about, like I said in the first slide, one of the first slides, we get about 1.7 gigabits. So you see on the y-axis on the right, that is our bandwidth in gigabits per second. On the left is our bandwidth in megabytes per second, base 2 megabytes. I tend to like base 2 megabytes, more useful when talking about files and stuff like that. But since we do have limitations on the network, we like to see gigabit is also handy to see. The x-axis here is how many listeners. We're going to defer that, just ignore that for now. We're going to see what that means on the next slide. And this tick mark up here that says iPerf UDP, that's just a reference point for about how fast I can go using iPerf with UDP between those two machines. So iPerf on those machines does not get up to 10 gig on its own. iPerf TCP does, of course, but the iPerf UDP, even if I run with parallel clients, that's about how fast it goes because the server is also only single threaded. If I run multiple instances of it, then you get up over 10 gig pretty quickly. But I just like keeping that as a reference point because I'm not hoping to get better than iPerf for single threaded performance. Okay. Okay, so this seems a little more legible. I changed my screenshots to try to make this appear better. So if you look at it when it's running in this situation, this is a pretty I think a thing that people are pretty used to seeing. This tool is called PRStat. It's like top on Solaris. It gives you a little bit different information, but same basic thing. It shows you the processes and how much CPU and other stuff they're using. So if you look at this and we're saturated, we're going as fast as we can go. But if an administrator looked at this box, you could barely even tell that it looks busy. We're using less than 10% of the CPU on the box. Our load average is under 1.5. We're not saturating the network because we just saw we have two 10 gig NICs and we're only hitting 1.7. We're not saturating the CPU. We're definitely not saturating the disk because everything is cached in memory. So if somebody, like if you went to your, the people handling your hardware and you said, we need this, like we want this to go faster. We have a file server that's serving a lot of data. We wish, it wouldn't be overloaded quite so easily. You say we need some faster hardware and you look at this, it says this machine isn't even breaking a sweat. What's the deal? This is another command called mpstat. Oh yeah, that's why I say it. So is the server even busy? Can you even tell? If you use mpstat, this is a different tool on Solaris, which is just reporting the per CPU usage. So the column on the far right is how idle we are. So in this situation, we are also, it doesn't look terribly stressed. The maximum CPU that we're using is only around maybe 40%. Nothing goes over 50%. And if you have someone that knows a little bit more about what they're doing on Solaris, there's another PRStat command which tells you the CPU usage per thread and will give you a little bit breakdown of the usage. Instead of just CPU usage, you can see user versus system versus a few other ones, which we're not going to pay attention to. They're not terribly relevant. So in this, it becomes a little more obvious what's happening. We have one thread that is using almost all of the CPU for a single thread, and all the other ones, those are the RPC threads, are doing almost nothing. The way that that first thread is identified as the RX listener, that's a patch. Technically, this is not unmodified master. There's one modification, which is to add that, which is just helpful when looking at these stats. It just identifies the listener for you. Yeah, so we can see that that's the listener. So if anybody doesn't know, the listener is the thread that we use for doing some network I/O. Sometimes, so it's called RX listener, RXI listener proc. The listener is how I informally refer to it a lot of the time. So in TCP-based protocols, anything that wants to communicate with a certain connection or a call or something like that, you accept a socket, or you accept on the listener socket, and then you get a new socket for communicating with that like session or that client. With UDP, we don't have separate sockets for every single call, at least not without some kernel support. So usually UDP-based protocols, you have some piece of code that reads in all the packets from the network, and then it has to parse all of those packets and see who they're for, and it hands it off to whatever thread or other work thing, whatever your model is. So that piece of code that does that for us, that reads in the packets, parses things, and does some processing is called the listener. It does some other processing too. It actually does a lot more than is probably necessary, but I'm going to defer that until later, into some later slides. But for all the stuff I said earlier, that doesn't sound, it's not terribly hard what it's doing. You're reading in stuff, you're parsing some things, you are looking some things up in structures, so there's some locks. But it doesn't sound too hard, but you have to keep in mind that it's doing it for all other threads in the system. If we have, so the -P option in the file server says how many RPC threads you have. Historically, that's typically 128 or 256 and 1/8. So even if we're only doing a little bit of work, we're doing it for 256 other threads. You also might wonder why the listener, which I said is the thing doing the receives, is being so tied up when the file server in this scenario, in this benchmark, is sending data. But the benchmark here is that we have a bunch of clients reading that that 1 megabyte file over and over again. So why are we spending all our time receiving stuff? And that's just, so some of that is because of, if we send data to the client, we have to wait for ACKs before we can send any more data. That's just how any protocol with the window will work. So we have to wait for the transmit window to clear up before we can send more stuff. So if we don't, so until we receive the ACKs, we cannot proceed. So there's a lot of, so since we're sending a lot of packets, we have to receive a lot of ACKs at the same time. So the first intuitive thing that you might want to do you see all this stuff is happening in one thread. We have 200, like 100, 200, 300 RPC threads. We can just break it up. We can just add more threads to use more cores. So that's simple enough to do. There are some code changes that need to be done, but you also have to consider that the receive message syscall itself, the thing that receives the packets from the network, even if you call that from multiple different threads, it will be internally serialized because the OS that implements this does some locking on the socket itself. Because if you have multiple threads, then we take some data from the NIC or from whatever buffer we have internally and hand it to one thread that's doing the receive. You hand it to the next one that's doing the receive. There's some resource contention there. But everything after the receive message, if we have multiple threads running the listener, everything after that can be run in parallel as we want because we control the code there. In the existing code, when they're in like existing OpenAFS and existing releases, since the listener is only one thread that ever runs, we only ever have one thread that does all of this, it makes a lot of assumptions that it is the only thread running all of this stuff. So there are certain resources that it doesn't have locks for and does not have like any guards over other threads trying to mess with the same stuff. So we have to introduce another lock, which I introduced per connection. This isn't the only way to do this. There's a whole bunch of ways to fix the locking and resource management. But the easiest way I thought was doing it per connection because most of the code paths in there deal with connections. Pretty much everything, there's very little code before you get a connection because basically all we're doing is trying to find which connection it's for. So there's an additional lock that's introduced in that. So if you have this idea of creating multiple threads, there's then the question of, well, how many threads do you make? You make 200, you make 2. I went for testing between 1 and 20 on this machine. So that's what the x-axis is here, is how many listeners we have. So listeners meaning like the listener thread. So this does not provide much of an improvement just by itself, probably because of some of the limitations I described. So this makes it look pretty bad because the graph is zoomed out so much. It is a noticeable improvement, but it's a little, it's not very much. It's not as much as you might expect. The reason it kind of goes up and down, I think, is just the, between runs, we get a little bit of variation on how fast it goes. But because we run it so many times, you can see a clear trend. And this trend is not going much of anywhere. So we look at some of the statistics, some of the CPU usage again. We are using more CPU. Most of the cores are now using more than half. And in the PR stat per thread output, you can see for these examples, I pull from the case where we have 10 threads. And you can see they're not quite using 100% CPU anymore. So the next thing to consider, or that I will be considering in this talk, is the overcall of all the syscalls that we need to make. If you look at this, this column over here, SCL, tells you how many syscalls per second that we're issuing. And that is quite a lot. Each listener thread is around 160,000. And not all, so some of those are for, like, obviously we have to issue syscalls for receiving packets, sending packets. A lot of them are for locks as well. The locking in Solaris causes a lot of syscalls. But regardless of that, even if all of that was improved or fixed, we certainly have at least one syscall that we must make to receive one packet, because that's receive message receives a packet. In addition, we also have locking to do for every single packet we get, because for every packet we get, we look up what every like data ACK packet. Because for each of those packets, we need to look up what connection it's for, and we need to look up which call on that connection it's for, and then typically we lock that call and do some processing inside the call. And in addition, all that is happening inside the listener. The listener is this thing that the processing time in there is kind of a precious resource because we only have a certain number of listeners for a lot of threads. Everybody's waiting on us to move on. Each packet we send is also a syscall, plus some locking. We tend to drop locks when we're sending packets. This also happens in the listener, which may be unintuitive. We don't need to send it in the listener, but we do currently. We're going to talk later about why that's happening. So we have to send, So this is, you might think this is unavoidable because we do have to send packets, and we have to send our data in separate packets. We can't tell the kernel, here's 50,000 bytes of packets, 50,000 bytes of data, please break it up into packets for us. However, there are a couple of syscalls that can be used to send multiple packets at once. This can be thought of as similar to like write-v, read-v, except it works on packets. They're sort of newish. Like that's not those OSs aren't terribly new, but it's not new in Linux 5 or anything like that. So they've been around for a while, but they made themselves available in these platforms a little more recently. And when we do this, so we get the benefits of reducing the overhead of the individual syscalls. So if we receive 1,000 packets at once, we don't need to call 1,000 syscalls. We can call one syscall and get 1,000 packets. We also can benefit from processing those packets all in bulk, all at the same time. So if we get if we get like 5 or 10 packets for the same call, you can look up that call and lock it, and then process those 5 packets without having to do the lookup and the lock overhead every single time. To make that more likely to happen, in the current submission, I do sort the packets according to the metadata in them. We could like hash them or some other, like there's other ways to handle that. I don't think that's, based on the things I've seen, that's not, we don't spend a lot of time sorting. So I don't think that's too impactful, but it is an area I haven't really looked at too much. And because of that, because of those improvements, when we like kind of bulk process packets, even on platforms where you don't have the receive mMessage and send mMessage syscalls, you still can see a lot of benefit because we avoid the locking overhead and processing overhead when receiving multiple packets in bulk. So in those cases, in the code, I do think I included the cases where if we don't have receive message available, we can still call receive message, the regular receive message, and you call it multiple times until there are no more packets available or you've run out of space. So we can emulate these syscalls if they're not available in the kernel. It's not quite as efficient, but it still provides benefit. So if we do that, we do see a pretty big change, particularly around 10 listeners. In a lot of these, we do start to see a turning point. There's a certain number of listeners where after a certain point, I think the performance just gets good enough where we're kind of keeping up with the traffic a little better. Before that point, things were a little bit slow, and when things are slow, sometimes they cause resource contention, and we keep trying to acquire the same blocks at the same times as other threads. And once we speed up a little bit, things become less congested, and we can move on a little bit faster. So now we are hitting about 9.2, 9.3 with at least 10 listeners, and after that point, the performance doesn't really change after that. You can see our CPU usage is now much higher, over 95% for all of the 16 cores in this machine. And our listeners still have, we spend quite a lot of time in system, so in kernel space. Our user space time is not that great. Our syscalls are lower, even though we are processing like 4 or 5 times as much data. So the syscalls are low. They're not that much lower, but since we're processing so much more, we're doing so much more, they are quite a bit lower than they would be otherwise. And you can see the RPC threads under that rectangle circle thing. They're getting a little bit higher now. They used to be all under 1% user plus sys. Now they're getting up to like 5. So the listener is still doing quite a lot in all of these, all the listener threads. So at some point, you have to actually look at it and see what is it doing, spending all of its time in there. This completely unreadable graphic is a flame graph. And it's a little fuzzy on the projector, so you can't read any of the text. So the flame graph is a pretty old technique, I think, for profiling things and looking at where time is being spent in functions. So what it does, the way that we generate this is using a dtrace script that just every so many times per second, like 900 times per second or something like that, we look at where the code is and we see what the call stack is for where we are in the code, and we increment a counter. And at the end, you see how many times you are in each of those call stacks. So the height here, like how tall something is, doesn't matter. How wide something is how much time we are spending in that particular area of code. So in here, the things that are highlighted in purple are send end message syscalls. And this flame graph is only for the listener, not for the entire process. So it's only for listener threads. And we are spending what I thought was a surprising amount of time in send message. It's 71.2% of the time, according to that. It's approximate. This is based on kind of probabilistic gathering of data, so it doesn't record the exact amount of time we're in there, but it's pretty hefty. So why are we sending so much in the listener in the first place? Normally in protocols like this, you would think if you write 5 bytes and then write 5 bytes and then write 5 bytes, you buffer that stuff in memory until you have a full packet, and then you can send it to the peer, ignoring things like Nagel's algorithm and stuff like that. But if you're just writing very, very quickly, you buffer stuff until you have a full packet, then you send the packet to the peer. And you can only send as many packets as your window size. In our case, we have like advertised window sizes and max window sizes, but regardless of what your window is, if you hit your max, you have to wait until the peer sends an ACK to say that it's received the packet, and then you can move on. The window advances, you can send the next packet in the buffer. So you would think that when the transmit window is full and we want to write something, we would wait for the peer to ACK until we can proceed. But that's not what happens in our RPC threads from a high-level point of view. If our transmit window is full, we don't actually wait. We keep filling it into about twice what the window size is. We don't send those packets because you can't send them, like that would violate the protocol. But we prepare the packets to send in the future, and we have them all buffered in memory. The listener then, when it receives the ACK from the client, from the peer, it can then send those packets immediately. It doesn't need to wake up the RPC thread for it to give you the next chunk of data. And so that's why the listener is sending all of these packets. Now, as for why we are doing this, it seems a little roundabout. I assume that this was originally done for a couple of reasons. One is that for LWP, for single-threaded operation, this is more efficient because it reduces context switches. And in LWP, you don't have multiple threads. There's only one thread, so there's no downside. We're all running on one CPU anyway. It also allows RPC threads to quickly move on to the next thing they have to do without having to wait for the peer to ACK all the data. So if you're very close to the end of the RPC, or very close to the end of sending all your data, if we buffer more than we can actually send at once, we'll buffer all the stuff into the RX call, the RX write function returns, and then we can return from the RPC, we can close our file handles, release our references to the volume, all that stuff, and so we can then get the next RPC and run another RPC. So in certain cases, that is, of course, faster, but we are currently, in the current state of the code as of this slide, we have some bottlenecks with the listener, so we want to shift some load off of it. And one way to do that is to stop sending packets, in this case, from the listener. So the technique that I had implemented is something I call deferring our calls to RxI start. So in the code, RxI start is the function that causes that looks through our packets and sees what we need to send and sends things that have not been sent and are within the window size. So in the listener, I make it so the listener doesn't call RxI start anymore. Instead, in all the places where it would normally call RxI start, we set a flag in the call indicating that RxI start needs to be called. And we wake up the thread that's inside Rx write, which is waiting for the window to advance. And that calls RxI start for us. We only do this when Rx write is waiting for the transaction window, or transmit window, sorry, keep saying that. And I said before, we don't wait for the peer to ACK everything, but we do still wait for ACKs to come in, but we just do so after filling the transmit window fuller than it needs to be. So another approach to this that I considered was, instead of shifting where the sends happen, we could just have all of the packets go to that thread. when a thread is waiting in RxWrite, it's not doing anything. We're just waiting to be signaled by the listener to be able to proceed. So while we're waiting, we could just do all the packet processing there. And I did try implementing that, but it ended up being slower, probably because it involves more wake-ups, more handing data between two threads. So that can be not very efficient. It also changes how we do the memory management of the packets, because the packets are no longer just in the listener. We kind of hand off the packet to a different thread, so that there's more to consider there with the memory management. It's also possible I screwed it up, and I need to look back and see how to fix it. But in this implementation, at least, we get a similar level, a similar peak performance as the previous step, but we hit it much more quickly in terms of increasing listeners. So we hit the peak at around 3 instead of 10. So that means, so you might think that doesn't, if it doesn't improve performance, is this really an improvement? This does reduce our reliance on needing to tune the server for a particular number of threads, which is nice. It also has effects in later patches, well, the next patch. We can see now the CPU usage is now very close to max, at 99 to 100% on all the cores. So that the number all the way on the right is the idle percentage.
Oh, that's idle percentage.
So they're all at 0 or 1, so we're using 99 to 100% of the CPU on all these. And the amount of system time for all the listener threads, of course, has gone way down because we've moved most or all of the send message syscalls away from the listener into the RPC threads. So you see the RPC threads are using much more CPU than they were before. The listeners are using much less, and the syscalls are much lower than they were before as well. They're now at like 70, 80,000 per second. And now, so earlier, in one of the earlier steps, I mentioned that receive message itself tends to be heavily serialized, but it's serialized per socket. So obviously, if you have two different sockets, they're not going to conflict with each other because they're usually different traffic. So if we could make separate sockets for each of the listener threads, that would alleviate some of the contention here. But of course, we have to be listening on the same IP address, same port, because that's where all the clients are talking to us on. So normally you can't do that. Obviously, you can't have two sockets on the same port, but there is a socket option that lets you do that for basically this reason, which is also somewhat newish. It's available in Solaris 11, 5.6.5, or somewhere in that area. I'm not completely sure of these version numbers. I didn't test back to see where it goes, but we had configure tests for that. And the way that it works, if you have 5 different sockets that are bound to the same address with that option turned on, then the kernel will, like all the packets that come in, will get sent to one of those 5 packets. One of those 5 sockets. And even if you're not reading from a socket, like it doesn't look to see, oh, this socket is full, and it pushes it to the next one. Like it picks one, and if you don't receive it on that socket, you'll never get it. The way it picks which socket it delivers it to is based on a hash, which typically, at least on Solaris and Red Hat Linux, I believe the default is for hashing on the IP and port for both the source and destination. It is configurable. And on Linux, it's configurable even to, like, you can define your own, like, BPF thing to say what it is or something like that. I don't think we have any reason to need to change that, but it's useful to know. So if we adding that is not terribly difficult. If we add that, we can see the performance does get bumped up a little bit. So now we can exceed 10 gigabits. And just to note, so I mentioned how the previous line, the O3 defer, the orange thing up there, didn't look too much better. The thing that's hard to illustrate with these graphs is that the last one, you see the improvement there, but if you only include one of those 2 patches, you don't see the improvement. It's only both of them at the same time. So if you look at our CPU usage, we are literally at 100% everywhere in that particular run. I'm also sorry this doesn't quite line up. That's how MPStat does output it. I didn't like mess with it. If that's not me that screwed that up. And if you look at the per thread CPU usage, we're down. So for the first time in all of these screenshots, our kernel usage, our kernel CPU usage is actually lower than the user for all the listeners. The RPC threads are much higher, and our syscalls are even lower than they were before. It's under 60,000 for all of them except for one, which is barely at 60. Okay. Okay, so that's how we achieve over 10 gigs. Let me go back to that slide actually. So yeah, so we do go over 10 gigs, 10 gigabit on that. Not very much over 10 gigabits, so obviously it's very, we're not hitting we're obviously not hitting 20 gigabit or anything like that. But the thing that's very nice to see about this is that it does use the cores. So if you have a more powerful server, more powerful meaning just more cores, not necessarily faster single thread performance, I do believe it will go faster, which is nice to see. And this benchmark that I've been dealing with is all, like what we're doing is fetching large amounts of data, large meaning about 1 megabyte. But a lot of traffic in file servers is for like fetching metadata. There are RPCs that are only maybe 100 bytes long. So we don't have that same code path where where we're reading data from disk and writing to the peer and like waiting for it to acknowledge our packets. Things like fetch status RPCs, they're very quick. So we get the RPC, the input arguments are all in one packet. We just do a little bit of processing and we push our response, which is also one packet. So there's no waiting for anybody there. So after we did all these patches, I wanted to make sure that I wasn't making those cases worse because they stress very different parts of the system. So just running the same benchmark, but with a much smaller size of RPC payload. You can see the results here, which do show we are better than our baseline performance. It does get worse as we add RX listeners, but it's like each listener doesn't make it that much worse. I believe it's worse because when we do this, when we institute these patches, we are like some code paths start to get like we're more quickly hitting things in parallel, and so we are hitting some resource contention when they try to like acquire the same resources, and when we do that in more threads, then things can get more clogged up and they go a little bit slower.
Question.
Yes.
Why do you think mix one is all over the networks?
Yeah, yeah. So it varies quite a lot.
And it gets better.
Yeah, I don't. Well, it getting better may be like a coincidence. It may just be going up and down all the time. Honestly, I haven't looked at it. I'm not sure.
Just one thing at a time. When we actually mix is what we deployed right now, right?
No. So the order in which these patches were developed is not the same as the order I'm talking about them here. This is for like convenience of a presentation. So the patches that I have submitted to Garrett and the patches that you guys had, they're all in a different order. I could submit them in this order. Like I have the rebased versions of the commits. I don't know if it really matters. So yeah, the first version you have doesn't have multiple threads. So that's why it doesn't show much of an improvement. Yeah, so some of the so far all the benchmarking I've done is mostly with default arguments to the file server. The only thing I change is the number of threads, just because the default is very low. So we also have to consider what other things in the file server may be impacting performance when when people actually run this. We run things in very different configurations. There's different options people may use. Most of them don't matter. It's a lot of things for adjusting sizes of caches. Number of callbacks, number of volume caches, that kind of thing. That doesn't really matter when we're all fetching the same file and have a relatively small number of clients. Like if we have a few hundred, that's not going to exceed the callback table. Oops. But some options do matter. One that matters quite a lot is the audit log subsystem. Oops. Click that. So if we turn on audit logging, specifically the System 5 message queue version of the audit logs, we see a big difference. So all the lines up above are the same as the previous graph, and I've added more that are the same color for each branch under it, but you can't really see it because we're zoomed out too far. So if we zoom in a little bit, you can see things actually get worse with these. So the baseline performance on the top line is the original one without the auditing turned on. The one under it is with auditing turned on. So obviously there's a performance impact there, and there's a performance impact on these changes, and they're more severe. So at the last, like the step 4 that I had before, the thing with everything, including the reuse port, it's not so bad. You know, we're 7 point, like the baseline is maybe 7.75. This is 7.25 megabytes per second. Oh, and yeah, I didn't mention, so megabytes per second when you're talking about these small RPCs, obviously that's much smaller than when you have large RPCs, when you have the large chunk size being fetched. The bandwidth here is actually not really what we're concerned with. Usually when you do these, you graph like packets per second or requests per second. But since I just already had the bandwidth graph, so I just kept using them. They're all, the trends are exactly the same if you graph like packets versus the bandwidth, because the packets tend to all be the same. The relevant packets are all the same size. So it's just multiplied by a certain amount. But yeah, so this is worse.
Is this for the small?
Yeah, sorry, this is the small RPCs. So the big RPCs is identical to the original graph. So I don't graph it because it looks exactly the same. Because the overhead, so we're gonna get into why this is happening. So the reason that this happens is the audit system uses one big global lock every time you go into the audit subsystem, and it's held across the calls when you build up, like when you construct the audit message and when you call the relevant syscall to put it in the audit log. So in this case, it's a system5 message queue. It's a message send call. And if you're using a regular file or something, that would be a write syscall. But it's held across that whole thing. So one thread will log an audit message, and then another thread will be doing something and has to wait for that thread to finish before it can continue. And when we add more threads and we get things processing faster in the RPC threads, they conflict with each other much more, and that's why things get a bit slower. The patches that I have submitted for this enhancement don't address this, but we do have a fix for this. Cheyenne Wills will be presenting tomorrow about some changes to the audit subsystem, which address this problem, specifically with the locking. And it introduces a new pipe interface, a new audit interface called pipe, which also, the design of that helps a bit better. But also there's some changes to the audit subsystem itself, but I don't want to steal too much from him. So I won't keep talking about that. But I should also mention, it's a little bit worse for the small RPCs, but the big RPCs is much better. So it's not all bad. Okay, so I want to talk about some lessons I've learned while doing this. I don't usually do like performance analysis, honestly. So I made some mistakes when I tried to do this a little too quickly. I tried to make some shortcuts at the beginning of this. So something I learned is that trying to record the actual runtimes of how long we're in each function, at least using dtrace probes, is way too heavyweight. When we did that, it did impact the performance of how fast we were running. And sometimes, so I figured that, you always assume that's going to be the case, but I thought that if it slows down everything, the relative performance, like if I make improvements, the relative performance would still show that it was better. However, that's not always the case. Sometimes different code paths are impacted much more heavily by this than others. And in fact, some of the branches that we implemented went faster when the profiling was turned on versus when it was turned off. So that was very confusing to see. I thought I mixed up things. And the reason for that was when things slowed down, sometimes our locks would not be, like we wouldn't be congesting on the same resource. So if you slow down just enough, the locks get taken very quickly because there's nobody else trying to acquire the same lock. So the code paths would go faster. That of course leads to the second point that I really needed to verify that the profiling was not impacting performance and was not impacting the numbers. Now I obviously make very special care to run without the profiling turned on to make sure that everything still matches up when I do that. And in general, you really need to test things. Don't assume things are not going to have effects. So at the start, I was using a couple of VMs. Actually, no. At the start, I was using a VM, and I was trying to do this. I was trying to do all the traffic through localhost, because then I thought, I don't have any bandwidth ceiling. Like a 1 gig card will have a 1 gig ceiling, 10 gig card will have a 10 gig ceiling, localhost is as high as you can get. But I thought that was the best option, but you have, since the clients and server are running on the same machine, they obviously conflict with each other, and it causes some different results, and you're not going through the same code path as you would in real life, because going through the local interface doesn't go through the NIC, it doesn't hit the driver, there's some stuff with interrupts that happens differently. And of course, as I just said, I wasn't running everything with audit log until the very end. So this is how we get, like I said, we got to 10 gig on that hardware. Some things that we could do to maybe go make things even better in the future. I have wondered about the ACK processing we have. I think other people have said before it's really not efficient what we do. There's like a linked list of packets that we traverse every time we need to process things. I haven't looked at that too much, so I don't know how big of an impact that is, but it's just an area that could use revisiting. We may want to look at jumbograms because a lot of the overhead is per packet. So if you can send however many thousand packets per second and you increase the packet size from 1,500 bytes to 9,000 bytes, then you're going to get the bandwidth will be that much higher. Most of the overhead and the speed limitations are per packet, either per RX packet or UDP packet, which are different. So the existing jumbograms, of course, are like this thing where we stuff 4 packets into one UDP datagram. I've been wondering about, maybe like if we could just find ways to just have larger packets instead of doing that. Have a 9,000 length packet instead of stuffing 4 1,500 byte packets into one. That'd be nice. AFRX RPC is the Linux implementation of a kernel-aware RX socket. So obviously, all the stuff I did here was on Solaris. We don't have that. On Linux, we could try to make use of that. This is implemented by the KAFS stuff that David Howells does. I haven't looked at how robust it is, if it works for us, if there's functionality we need it doesn't have, I don't know. But that is certainly something that would help because that would do that can do the interpretation of the packets, and the demultiplexing to our different calls could happen in the kernel, where we have much more control. Things can go a lot faster. We don't have to have dedicated threads to do that. Another future direction this could go in would be doing these similar improvements to here in the kernel. Everything I've talked about so far is just implemented for pthreads, and one of them also works for the kernel, but I haven't really tested to see what the impact is. So some workloads, you may want this for client stuff as well. That was just not the focus here, so I didn't really look at it. And of course, if you just use TCP directly, we don't need to do any of this ever. Well, that's not quite true because it's just payload that goes over TCP. But a lot of this you can just ignore, and you could use existing software that works pretty well, and we don't need to mess with it. So the code for this, that commit is the top commit that has everything in it. All the different steps that I said are in those different topics. Send message and receive message is split out, but everything else is organized the same as it was here. I originally submitted some of them as drafts to Garrett, which we usually don't use. I wasn't sure exactly how they worked. I was trying to avoid submitting 20 patches all at once. I was trying to limit it a little bit, but when I went to do this presentation and I clicked on these links, I noticed that Garrett makes you log in to view those. So I'm not sure if other people can even look at them. Do I have to mark them not as a draft, or do I just?
I think you can mark them as a draft, or there's also a way to specifically share this draft with this person.
Can I share it with everybody? I don't know. So that was, I don't need an answer right now. That was something I was just going to explore while we're here. So these might be public. So I'm sorry if these are not available right now. I didn't mean to do that. Yeah, and slides are there. Okay, somebody else talk, please. Yeah, questions if you have any. Otherwise, I need to rest my voice. All right.